When you are learning security architecture, it can feel like the only way to know whether a design is safe is to build it, deploy it, and then see what breaks. That approach is risky because production is the most expensive place to discover that trust boundaries are wrong, that sensitive data flows are uncontrolled, or that a dependency failure causes unsafe behavior. Modeling and simulation are ways to explore how a system might behave under different conditions before those conditions happen in real life, so you can expose security failures early while changes are still relatively cheap. Modeling means creating a simplified representation of the system that helps you reason about trust, data flows, identities, and boundaries. Simulation means running scenarios against that representation or against a controlled environment to see how the system responds when assumptions are stressed. The goal is not to predict every possible attack, but to find likely failure patterns and fix them before real users and real attackers are involved. This episode explains how modeling and simulation support security architecture, what kinds of failures they can reveal, and how beginners can translate what they learn into clearer requirements and stronger design decisions. When you get comfortable with this, you stop treating security as a last-minute inspection and start treating it as something you can test in advance. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first thing to understand is that modeling is about purposeful simplification, not about creating a perfect replica of the system. A model should include the elements that matter to the question you are asking, such as users, services, data stores, and the flows between them. It should also include trust boundaries, because most security failures happen where trust changes, like when untrusted input crosses into a trusted service or when a service requests data from a sensitive store. For beginners, a simple model might focus on a single workflow, like user sign-in and data retrieval, rather than trying to capture the entire enterprise. Even a small model can reveal whether identity claims are validated, whether authorization is enforced consistently, and whether sensitive data travels through unnecessary components. A model can also capture assumptions, such as which networks are considered trusted, which services are privileged, and which components are allowed to talk to each other. By writing those assumptions into the model, you make them visible and easier to challenge. This visibility is valuable because many real systems fail due to hidden assumptions that no one realized were being made. Threat modeling is one type of modeling that many people learn first, and it is especially useful because it helps you reason about how a system could be harmed. You can represent the system and then apply threat categories like spoofing, tampering, and information disclosure to each key element and boundary. The value for architecture is that it forces you to consider different attack paths and then decide what controls must exist to block those paths. Even without deep technical simulation, the act of mapping threats to boundaries can reveal missing enforcement points, overly trusted components, or unclear data classification. For example, if the model shows that an external client can send requests directly to a data service without passing through an authorization enforcement point, that is a design failure you can fix before implementation. If the model shows that sensitive data is sent to multiple downstream services unnecessarily, you can reduce exposure through redesign. Threat modeling is sometimes treated as a paperwork activity, but when used as a true model, it becomes a design tool that exposes security problems early. The important part is to connect the model to real architecture decisions and to write down the mitigations as requirements that can later be validated. Simulation expands on modeling by introducing change and stress, because many failures only appear when conditions are not normal. A simulation can be as simple as walking through a scenario step by step and asking what happens when inputs are malicious, when a dependency fails, or when an attacker has stolen credentials. You can simulate different roles and identities trying to perform actions they should not be able to perform. You can simulate unexpected sequencing, such as skipping steps in a workflow or repeating actions rapidly. You can simulate partial failures, like a service timing out or returning inconsistent data, and see whether the system fails safely or fails open. The key is that simulation is not random. It is guided by the model's boundaries and assumptions. If an assumption is that a service will always validate tokens, you can simulate what happens if token validation is misconfigured or inconsistent. If an assumption is that a network segment is isolated, you can simulate what happens if an attacker reaches it through a compromised workstation. These simulations help you see how the system behaves when assumptions are violated, which is exactly where security failures live. One of the most valuable uses of modeling and simulation is exposing trust boundary confusion, which is when components trust inputs or identities more than they should. Trust boundary confusion often shows up when a service accepts a user identity claim without validating where it came from, or when authorization is enforced only in one place and bypassed in another. In a model, you can mark which components are responsible for authentication and which are responsible for authorization, and then simulate requests arriving through different paths. If the simulation shows that certain paths do not pass through the enforcement point, that is a failure. Another common issue is trusting internal traffic too much, assuming that anything inside is safe, which breaks down when attackers gain internal access. Simulation can reveal how quickly an attacker could move if internal services do not authenticate each other or if privileges are too broad. When you see that, you can redesign boundaries so each service verifies identity and enforces least privilege. This is the kind of architectural improvement that reduces entire classes of vulnerabilities rather than only one bug at a time. Data flow modeling and simulation can also expose information disclosure failures that would be hard to notice in feature-focused reviews. A design might function correctly while still exposing data in unintended ways, such as returning too much information in search results, logs, or exports. By modeling where sensitive data originates and where it is consumed, you can identify whether data is minimized, segmented, and protected across flows. Simulation can then explore what happens when an unauthorized identity attempts to access data, or when a component that handles data is compromised. You can ask whether encryption is required across certain boundaries, whether data is masked or filtered in outputs, and whether sensitive data appears in error responses. You can also simulate the compromise of a downstream service and assess what data it would have access to, which reveals blast radius. This helps you decide where to place stronger controls, like restricting data access to only necessary services and enforcing fine-grained authorization at query points. The earlier you make these decisions, the less likely you are to discover in production that you built a system that leaks data by design. Modeling makes data exposure visible, which is the first step toward reducing it. Availability and resilience failures are another area where simulation is powerful because denial of service and cascading outages often follow patterns that are hard to see on diagrams. A model can show dependencies, such as which services rely on which other services, and which ones are critical to essential workflows. Simulation can then explore what happens when a dependency slows down or fails, and whether the system degrades gracefully or collapses. From a security perspective, availability failures matter because they can stop critical services and can also trigger unsafe behavior, like bypassing controls to restore functionality. A simulation might reveal that a single external service outage causes internal services to time out and crash, creating widespread disruption. It might reveal that retry behavior amplifies load and turns a minor incident into a major outage. These findings lead to architecture requirements like timeouts, circuit breakers, rate limiting, and fallback behaviors that preserve safety. Even though these sound like reliability topics, they are security relevant because availability is a security property and because unstable systems are easier to exploit. Simulation lets you explore failure modes before users suffer them. Another important category is configuration and deployment model behavior, because many security failures come from how systems are deployed rather than how they are coded. Modeling can include deployment boundaries like public and private networks, identity providers, and administrative access paths. Simulation can explore what happens if a service is accidentally exposed to the internet, if a default setting is too permissive, or if an environment variable changes how authentication works. The point is not to assume these mistakes will happen, but to accept that they are plausible and to design guardrails that reduce harm. For example, if accidental exposure is a risk, you might require that sensitive interfaces enforce authentication regardless of network location. If default settings can be unsafe, You might design for secure defaults and require explicit actions to relax them. Simulation helps you test whether the architecture depends on fragile configuration assumptions or whether it is resilient to common misconfigurations. A design that remains safe even when some configuration is wrong is a stronger design. Modeling and simulation help you move toward that strength. To use modeling and simulation effectively, you need to translate what you find into testable requirements and design changes. Otherwise, the exercise becomes interesting but not impactful. If the model reveals that authorization is inconsistent, you create requirements about where authorization must be enforced and what conditions must be checked. If simulation reveals that compromise of one service exposes too much data, you create requirements about least privilege and segmentation that limit access. If simulation reveals that failure of a dependency leads to unsafe behavior, you create requirements about safe failure and resilience patterns. These requirements should be written as observable behaviors, such as denying unauthorized requests, filtering data outputs, requiring validated service identities, and preserving consistent state under failure. You then use those requirements to guide implementation and acceptance testing. This creates a feedback loop where modeling reveals risk, simulation demonstrates how it manifests, and requirements drive fixes that can later be validated. The result is a design that is more likely to behave as intended in production. For beginners, this also builds confidence because you are not relying on intuition alone. You are using structured exploration. It is also important to manage expectations about what modeling and simulation can and cannot do. They cannot guarantee that no vulnerabilities exist, and they cannot perfectly predict every attacker tactic. What they can do is reduce surprises by exposing common failure patterns that are driven by architecture decisions, such as misplaced trust, weak boundaries, excessive privileges, and fragile dependencies. They can also improve communication because models provide shared diagrams or representations that teams can discuss without ambiguity. This shared understanding prevents mismatched assumptions, which are a major source of security gaps. Modeling and simulation are most effective when they are repeated as the system changes, because new features and dependencies create new paths. Over time, the practice becomes part of how you design, not a special event. That is a hallmark of mature architecture. Security is integrated into design exploration, not appended later. The central takeaway is that modeling and simulation are ways to bring security validation forward in time, before production makes mistakes expensive and dangerous. By building simplified representations of the system, focusing on trust boundaries and data flows, and simulating stress scenarios like malicious inputs and dependency failures, you can reveal where the design's assumptions break. Those discoveries then become concrete, testable requirements and design improvements that reduce exposure, reduce blast radius, and improve safe failure behavior. This is not about predicting the future with perfect accuracy. It is about systematically exposing plausible failure modes and fixing them while you still can. When you develop this habit, you start seeing architecture as something you can probe and validate, not just something you document. That shift makes you a stronger security architect because you are designing with evidence, not only with hope. In the next areas of study, you will build on this by applying review methods and analysis approaches that catch design flaws even when automated tools cannot, creating multiple layers of confidence before anything reaches production.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.